In our last video, we finished off talking about uranium and some of the element's isotopes. What we did not mention was the great difference between the number of protons and the number of neutrons. For example, uranium-238 has 92 protons and 146 neutrons. As you can see, there is a much greater difference in the number of protons and neutrons than what we had seen in smaller nuclei, such as helium or lithium. A chart of nuclides is one way of comparing the number of protons versus the number of neutrons in various isotopes. There are many things that can be learnt from one of these charts. First, notice the black squares present in the center throughout the chart. These are isotopes which are most stable and exist in nature. Notice the green line. This shows a path throughout the chart where the neutrons and protons would be in equal amounts. Since we see most isotopes on the bottom side of this line, we notice that the number of neutrons compared to protons increases as the atomic number increases. We call the black region the belt of stability or the valley of stability. In this region, the nucleus of each element is most stable and will tend not to go through any changes. The region above the black boxes are said to be proton-rich, as they have more protons than the most stable isotopes. The region below the black boxes are classified as neutron-rich. These have more neutrons than the most stable isotopes. When a nucleus is unstable, it will go through processes that will ultimately increase its stability. In the image we see here, the nuclei from the proton and neutron-rich sections will undergo changes to move into the belt of stability. Let us examine carbon-14, for example. We know carbon isotopes 12 and 13 are the most stable and fall in the belt of stability. This means that carbon-14 is neutron-rich. A neutron-rich nucleus will typically go through a process called beta-minus decay. This involves the change of a neutron into a proton. When this happens, an electron is released or radiated along with an electron antineutrino. Let's take a look at where carbon-14 sits in the chart of nuclides. Through beta-minus decay, this nucleus loses a neutron and gains a proton. This means there are now 7 protons and 7 neutrons, making this nucleus a nitrogen isotope. As carbon-14 and nitrogen-14 both have an atomic mass number of 14, they are referred to as isobars, meaning they have the same number of nucleons. A similar situation happens to proton-rich nuclei. An atom may undergo beta plus decay, causing a proton to become a neutron and emitting a positron, which is essentially an electron with a positive charge, and an electron neutrino. As an example, carbon-11 that undergoes beta plus decay becomes boron-11. These two nuclei are isobars, as they both have the same number of nucleons. There is also a third type of beta decay which occurs in a proton-rich nucleus, and it is called electron capture. As the name implies, electron capture occurs when an electron is absorbed by a proton. The positive and negative charges cancel out, and the change results in a neutron. In the process, an electron neutrino is also emitted. These 3 decays are all types of beta decay because they involve a beta particle, whether it be an electron or a positron. Gamma decay is produced when a high-energy nucleus releases energy due to a rearrangement of its nucleons. This energy is released using a photon. There is no change to the number of protons or neutrons. The final type of decay we will talk about is alpha decay. As mentioned before, an alpha particle consists of 2 protons and 2 neutrons, just like a helium nucleus. Alpha particles are very stable and will be emitted most commonly from large nuclei, such as uranium. When an alpha particle is emitted, the number of nucleons is reduced by 4, that is, 2 protons and 2 neutrons, and therefore becomes a different element. These 3 mentioned decays are the most common forms of ionizing radiation, which we will talk about in the next video.